Hi there, geometry friends. I hope that you are well. Here we go, another little bit of geometry. We are almost at the end of the school year, you guys. This is the last unit that not the last lesson, but the last unit. It's getting close, y'all. So the last time we talked about 45, 45, 90 triangles or isosceles right triangles. How about you pause this video and do this warm-up? Go. Alrighty, welcome back. So all three of these triangles are isosceles right triangles. Notice that they have right angles, so they're right triangles, and then they're all marked with 45-degree angles in all of the other vertices. That makes them isosceles right triangles, or 45, 45, 90s. The last time we talked about being able to look at what seems to be a weird way of writing a number, something like this here, and getting comfortable with it, because if we express a number like that, sometimes there's some shortcuts to right triangle side lengths that can be pulled just out of that information. We don't have to calculate anything. For example, in number 1, if I know the hypotenuse of this 45, 45, 90 triangle is 4 times the square root of 2, which is just a way you say that number, 4 times the square root of 2, then I can recognize that there's a postulate that says that a hypotenuse of an isosceles right triangle is where you take the side length and multiply it by the square root of 2. The side length multiplied by the square root of 2. And so if we want to find x, which is the side length, we know x equals 4. Done. This side's 4, this side's 4. We get it from right here. And that is it. There's all that is to it. These two lessons, the one about isosceles right triangles and the one we're going to talk about today, are only difficult if you make them difficult. They're really quite simple. You just pick up the information and put it in the place that it makes sense. In number 2, we notice that we have a side length of 3, and the postulate says in a isosceles right triangle, the hypotenuse is the side length times the square root of 2. And so x is 3 times the square root of 2. Done. Nothing more to be done. And the last one, the side length is 5, and so the hypotenuse is 5 times the square root of 2. And that is all there is to it. That's how you do those. All 45, 45, 90 triangles are going to work like that. So how about you update that notebook? Let's see, questions, summaries, making a new note page, all that good stuff. Alrighty, here we go. So the essential question today, what is the relationship among the side lengths of 30, 60, 90 triangles? And the topic is finding side lengths of 30, 60, 90 triangles. So this is the other kind of special right triangle that we're going to talk about. And we're going to use 30, 60, 90 triangles to launch ourselves into a little bit of trigonometry here pretty soon. So we're getting close. In the last lesson, we talked about isosceles right triangles and the shortcut to find the lengths of sides. This is what we did when we did the warm-up. That is, if you have a right angle and you either know this information, that two sides are, the legs are congruent, or you know that two angles are 45 degrees, or actually it just takes knowing one angle is 45 degrees, because of course that means the other one is too. That's all you need to know to find the side lengths if you know one of the sides. And there's no calculations to be done. If I know that this leg is 7 units, then I know that that leg is also 7 units because it's an isosceles triangle and two sides are going to be the same. The hypotenuse is going to be 7 times the square root of 2, because I know in every isosceles right triangle, in order to find the hypotenuse, you just put the side length next to the square root of 2, and that's it. That's all there is to it. And I can go the other way with this. If I know that the hypotenuse is 27,000 times the square root of 2, then I instantly know the side length, because it's just sitting there next to the square root of 2. This side is 27,000, and so is this one. And we're done. I know the side lengths just by pulling that information. And this is why having exact answers or square root represented numbers can really be helpful, because if you turn these things into decimals, you stop seeing the patterns. And patterns are good. So today we're going to look at another specific triangle and find shortcuts for finding the lengths of its sides. It's called a 30, 60, 90 triangle, and it's called a 30, 60, 90 triangle because, well, you know, it's got 30 degree, 60 degree, and 90 degree angles in it. A 30, 60, 90 triangle will look like this. It'll have a 90 degree angle in one spot, a 30 degree in another, making this one a 60 degree angle. And so you have it. A 30, 60, 90 triangle is a triangle. I left out a word. A right triangle with acute angles that measure 30 degrees and 60 degrees. That's the basic idea. A 30, 60, 90 triangle is very aptly named because it tells you exactly what its angle measures are. And so we have a triangle postulate that goes with this. The 30, 60, 90 triangle postulate says this. In a 30, 60, 90 triangle, the hypotenuse is twice as long as the shorter leg, and the longer leg is the square root of 3 times as long as the shorter leg. So that's a little more to take in than the 45, 45, 90s or isosceles right triangles. So it's kind of broken down here. Your hypotenuse is going to be the shorter leg times 2. That's basically the idea. And that's, so you see that here, the hypotenuse, the one that's directly across from the 90 degree angle, is 2 times the shorter leg. And then the longer leg, the other leg that's left, if you take the shorter leg and multiply it by the square root of 3, and you will get that length. So everything depends on knowing what the shorter leg is in this one. So how can we always tell what the shorter leg is? Well, the shorter leg will be across from the 30, wow, that's the worst 3 ever, 30 degree angle. Every single time. The shorter leg will be across from the 30 degree angle. And so just like when we draw an arrow across to find the hypotenuse, we can do the same thing and find the shorter leg. And once you know that, everything else is just putting the right pieces in. So let's do a couple of examples so you can see what I'm talking about. So the idea here is that if you know the shorter leg, the one that's across from the 30 degree angle of a 30, 60, 90 triangle, then you can always find the other side lengths because you take the short leg times 2, and that's going to be the hypotenuse, and you take the short leg times the square root of 3, and that's going to be the long leg. Okay? Now, if you've got a triangle that's got a 90 degree measure here and a 30 degree measure there, that's really all you need to know because, of course, this angle up here will be 60 degrees because in all triangles, all the angles have to add to 180. So you don't really need that information. Sometimes it's there, sometimes it's not. So look for that 30 degree angle and then look for the side that is across from it. Now we see that in this particular right triangle, that measure is 7. Well, if we want to know the hypotenuse, which is the one that's across from the right angle, we're just going to take that 7 and we're going to multiply it by 2. So instantly we know that the hypotenuse is 14. Now there's only one leg left. We call it the long leg. And all we have to do is take the measure of the short leg and multiply it by the square root of 3. So 7 times the square root of 3. Done. That's it. Now you know the lengths of all the sides. 30, 60, 90 triangles have a slightly more complicated shortcut than isosceles right triangles, but it's still a pretty nice shortcut, and it will work this way every single time. Now, let me see if I want to talk to you about that yet. Yeah, I do. So, what if, get rid of some of this stuff. Okay. What if I know this instead? Here. What if it was set up like that? Well, it's slightly different, but remember that if you've got a 90-degree angle here and a 60-degree angle there, then this one has to be 30 degrees because all three angles of any triangle sum to 180, and that's how you can find that 30-degree angle. The 7 is still across from it, so that's your short leg. The hypotenuse is still across from the 90, and so you know that that one's still 14, even though it was set up differently. And the third leg is 7 times the square root of 3. So no matter what, you're still going to be able to rely on the short leg. It's just that you might not have that 30-degree angle in there, and that's okay. All right, now let's talk about this. So we can use the Pythagorean theorem to see these relationships. These relationships are so strong and they are related to the Pythagorean theorem that they're just going to kind of pop out of the Pythagorean theorem. Now I want to tell you, I'm not going to ask you to do what we're about to do ever in class, but I just kind of wanted to show you how the Pythagorean theorem relates to what we're talking about, because kind of the whole theme of this unit is, where does the Pythagorean theorem crop up? So if I want to find the side lengths of any right triangle, I can use the Pythagorean theorem, and I can say that a squared plus b squared equals c squared, and I can just pop the information in there. Okay, so here's what I'm going to do. I'm going to have, I have this 30, 60, 90 triangle, and I've set it up so that I have a squared. I'm just going to use the Pythagorean theorem. You'll see what I'm talking about in just a second. A squared plus b squared. Now I know in a 30, 60, 90 triangle that the hypotenuse is 2 times the short leg. Well, here's the short leg, and here's 2 times the short leg. So I'm going to pop that right here. Oops, I forgot the squared there. 2a squared. Okay? So now I'm going to do a little simplification. I've got a squared plus b squared on this side. Can't simplify that. But 2a squared is going to be 4, because 2 squared is 4a squared. We good so far? I'm just manipulating using the Pythagorean theorem a little bit, and you'll see these relationships here come out of it. So then if I've got I've got an a squared here and an a squared here, and so I'm going to subtract an a squared from both sides. That's going to get rid of it on this side, and I have b squared equals 3 a squareds. Good so far? Now if I want to figure out what b is, I just take the square root of both sides. I can take the square root of b squared, and that's b. And I can take the square root of 3a squared, and I can separate that out. Square root of 3, square root of a squared. And then the last step is to tell you that b, this other leg, the longer leg over here, is a times the square root of 3. And that's how we get that whole thing out of the Pythagorean theorem. I sort of doubted myself when I was talking to you about this and putting this in the video, and I hope it wasn't too confusing. Maybe it was. Maybe it was dumb to put this in the video, but it's in there now, and I actually don't know how to edit it. So just fast forward this part if you don't like it, or forget about it completely. But I just kind of wanted to show you that we can go from the Pythagorean theorem to this idea right here. And we don't even need to use numbers to do it because the relationship is so strong and it comes from the Pythagorean theorem in the first place. All right, anyway, back to an example because that's what you're going to need to know, right? So we're going to find the values of x and y, and we're going to write our answer in simplest form. Simplest form is things that look like, you know, something times the square root of 3 or times the square root of 4 or whatever. That's what simplest form means. So it looks as though this is a right triangle, so that's good news. And then across from this 30-degree angle is a 9, and that 9 is sitting on the shortest side because the shortest leg is always the one across from the 30-degree angle. Now, if I want to find the length of the hypotenuse, which is the one that's across from the right angle, I just use this part. I take the shorter leg, which is 9, and I multiply it by 2. And so y is 18. That's the length of the hypotenuse. And then I take the shorter leg and multiply it by the square root of 3 to get that other leg that's left. So 9 times the square root of 3, and we're done. That's all there is to it. Y equals 18, and x equals 9 times the square root of 3. Done. Let's do a couple more just to make sure you're good. So let's see. I'm going to set this up here like that. And we're going to find the lengths of the other sides that are left. And this is a right triangle. So this is a 30, 60, 90 triangle. Now across from that 30-degree angle, we don't have very much information. But what we do know is the hypotenuse is 20. Now, if you take the shorter leg and multiply it by 2, you get the hypotenuse. So that means that I can take this hypotenuse and divide by 2 to get the shorter leg. So the shorter leg is 10. And then to get that last side, I just take that 10 and put it by the square root of 3, and that is done. In the second triangle, let's see. I've got a 60-degree angle, and I'm going to play with this and say that I know that this side is 7 times the square root of 3. Well, across from my 30-degree angle, I don't have anything, but I know that the long leg is the short leg times the square root of 3. And so this is the measure of the short leg. Done. And then if I want to get the hypotenuse, I just multiply that by 2. And we're done finding side lengths. These are nice little shortcuts, and they'll work every single time. All right, you guys, that's about it. Your practice is on quizzes. Again, it is not a quiz. Do not worry. I hope you have a wonderful day. Let me know if I can help you. Bye.